Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're the kind of person who finds comfort in the mysteries of the ocean rather than counting sheep. Either way, tonight's journey is just for you. You have nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light, as if the ocean itself is gently cradling you. Because tonight we aren't simply looking at the sea. We're diving deep beneath the waves, down to where the Earth's crust splits open, where molten rock meets freezing water, and where volcanic fires burn silently in the darkness. We're exploring the hidden world of deep-sea volcanoes, a realm of black smokers and mineral chimneys, of pillow lavas cooling in the abyss, and of life thriving in places we once thought were lifeless. Beneath the ocean's surface lies the most active volcanic zone on our planet, a place where new seafloor is born every day, where water can reach temperatures hot enough to melt metal yet never boils, and where creatures have learned to survive without a single ray of sunlight. Some of what you hear tonight may surprise you, or at the very least spark some quiet curiosity as you drift towards sleep. And just before we begin, if these calm, educational explorations help you unwind, or give you a peaceful way to end your day, consider liking and subscribing to the channel. It helps others find their way here too, one peaceful soul at a time. Now let's begin our descent into the volcanic deep. When most people think of volcanoes, they picture towering mountains with glowing red lava flowing down their sides, ash clouds billowing into the sky, and explosive eruptions that light up the landscape. They think of places like Mount St. Helens or Mount Vesuvius, dramatic and destructive, rising high above the land. But the truth is far more fascinating and far quieter than that. The most active volcanoes on Earth, the ones that shape our planet more than any others, are hidden beneath the ocean's surface. They don't make the news, they don't threaten cities or disrupt air travel. They simply exist in the darkness, miles below the waves, doing their ancient work in silence. Most of Earth's volcanic activity happens underwater. In fact, more than 70% of all volcanic eruptions occur on the ocean floor, in places humans have rarely visited and can barely imagine. These aren't the explosive, ash-spewing giants of land. Instead, they are gentler, more persistent creators, slowly building the very foundation of our ocean basins. Down there where the pressure is immense and the darkness is absolute, the Earth's crust is in constant motion, pulling apart in some places, colliding in others, and everywhere releasing heat and molten rock from deep within the planet. The scale of this hidden volcanic world is almost impossible to grasp. Imagine a mountain range that wraps around the entire globe, stretching for more than 65,000 kilometers, longer than any feature on land. That's the mid-ocean ridge system, a continuous chain of underwater volcanoes that winds through every ocean on Earth. It's the longest mountain chain on our planet, and it's completely submerged. Along this ridge, tectonic plates are slowly spreading apart, creating gaps where magma from the Earth's mantle wells up to fill the space. As this molten rock meets the cold ocean water, it solidifies, forming new seafloor in a process that has been happening for hundreds of millions of years. This mid-ocean ridge isn't one single mountain. It's a complex system of valleys, peaks, and volcanic vents, all hidden beneath thousands of meters of water. In some places, the ridge rises close enough to the surface to form volcanic islands, like Iceland, where the mid-Atlantic ridge actually breaks through the ocean's surface. But for most of its length, the ridge remains deep underwater, a place of constant creation where the ocean floor is being born, inch by inch, year after year. And then there's the Pacific Ring of Fire, that famous horseshoe-shaped zone of volcanic and seismic activity that surrounds the Pacific Ocean. While many people know about the volcanoes on land that make up this ring, fewer realize that it extends deep underwater, where submarine volcanoes dot the ocean floor in enormous numbers. These underwater volcanoes are formed in a different way than those along the mid-ocean ridges. Instead of plates pulling apart, here they're colliding, with one plate diving beneath another in a process called subduction. As the descending plate sinks deeper into the Earth, it heats up and releases water trapped in its minerals. This water rises into the overlying mantle, lowering its melting point and causing magma to form. That magma then rises through the crust, creating chains of underwater volcanoes that can stretch for thousands of kilometers. The Mariana Arc in the Western Pacific is one such chain. a line of more than 40 submarine volcanoes extending north of Guam. Some of these volcanoes rise thousands of meters from the seafloor, but still don't break the ocean's surface. They remain hidden, known only through sonar mapping and the occasional visit from a deep-sea submersible. These seamounts, as they're called, are scattered throughout the oceans by the hundreds of thousands. Scientists estimate that there may be more than 100,000 seamounts in the Pacific Ocean alone, most of them volcanic in origin, most of them unexplored. What makes these underwater volcanoes so different from their terrestrial cousins is the environment in which they erupt. On land, lava flows freely, gases escape explosively, and ash shoots into the atmosphere. But underwater, the immense pressure of the ocean changes everything. At depths of 2,000 or 3,000 meters, the pressure is so great that gases can't expand and escape the way they do on land. Water pressure suppresses the explosive release of volcanic gases, so eruptions tend to be quieter, more effusive. The lava oozes out rather than exploding, and it cools so quickly in the frigid water that it takes on entirely different forms. The ocean floor is in many ways a record of this volcanic activity. Everywhere you look on the deep sea floor, especially near mid-ocean ridges, you'll find evidence of past eruptions. Layers of basalt, the dark volcanic rock that makes up most of the ocean crust, cover vast expanses of the seabed. This rock didn't arrive all at once. It accumulated slowly over millions of years, one eruption at a time, building the foundation upon which sediments would later settle and life would eventually flourish. And yet, for all this activity, most of us will never see a deep-sea volcano. They exist in a world too remote, too dark, and too hostile for casual exploration. The pressure at these depths would crush a human body in an instant. The water is near freezing, just a few degrees above 0 Celsius, yet nearby vents can release fluids hot enough to melt lead. It's a world of extremes, a place where the rules seem different, where life and geology interact in ways we're only beginning to understand. But it's also a world of quiet beauty. Imagine descending in a submersible, the sunlight fading as you drop deeper and deeper, until finally, all light is gone and you're surrounded by complete darkness. Your lights sweep across the seafloor, illuminating fields of pillow-shaped rocks, strange formations that look almost organic, like a landscape from another planet. Steam or mineral-rich water shimmers in your lights, rising from cracks in the seafloor. And then in the distance you see it, a towering chimney, sometimes as tall as a 10-story building, with dark plumes of mineral-laden water pouring from its peak, like smoke from a factory. This is the world of deep-sea volcanoes, a place where Earth's inner heat meets the ocean's cold embrace, where new crust is constantly being born, and where some of the most extreme and fascinating ecosystems on our planet have learned to thrive. It's a world that reminds us how little we truly know about our own planet, how much remains hidden in the depths, waiting to be discovered. And tonight, as you drift towards sleep, we'll explore this hidden realm together, gently and calmly, one fascinating detail at a time. To understand deep-sea volcanoes, we need to understand the Earth itself, the way it moves and breathes and reshapes its surface over vast spans of time. Our planet isn't static. Beneath the thin shell of crust we live on lies a churning, molten interior, and that heat and movement drive everything that happens at the surface, including the formation of volcanoes beneath the sea. The Earth's crust is broken into enormous pieces called tectonic plates. These plates float on the partially molten layer below, called the asthenosphere, and they move, though so slowly that you'd never notice it in a human lifetime. They drift apart in some places, collide in others, and slide past each other along great faults. This movement, driven by convection currents in the mantle, is what creates most of the volcanic activity we see, both on land and underwater. At mid-ocean ridges, two plates are pulling apart from each other in a process called seafloor spreading. As they separate, they create a gap, and magma from the mantle rises up to fill that gap. Think of it like pulling apart two pieces of bread and watching the soft cheese in the middle stretch and ooze into the space between them. The mantle beneath the crust is hot enough that when the pressure decreases, even slightly, it begins to melt. This molten rock, or magma, is less dense than the solid rock around it, so it rises buoyantly toward the surface. When this magma reaches the seafloor, it erupts, but not in the violent, explosive way you might imagine. The pressure of thousands of meters of water above prevents gases from expanding rapidly. Instead, the lava flows out relatively gently, spreading across the seafloor and cooling quickly as it meets water that's barely above freezing. This newly formed rock becomes part of the ocean floor, and as the plates continue to move apart, more magma rises and more new crust is created. It's a continuous process, one that has been building our ocean basins for hundreds of millions of years. The Mid-Atlantic Ridge is perhaps the most famous example of this process. It runs down the center of the Atlantic Ocean, from the Arctic to the Southern Ocean, a distance of over 16,000 kilometers. Along most of its length, it sits at depths of about 2,500 meters below the surface. The ridge itself is actually a series of ridges and valleys, with a central rift valley where the spreading is most active. This rift valley can be several kilometers wide and hundreds of meters deep, a great crack in the ocean floor where you can sometimes see fresh lava flows, still glassy and unweathered. The rate at which these ridges spread varies. The Mid-Atlantic Ridge spreads relatively slowly, at about 2 to 5 centimeters per year. That might not sound like much, but over millions of years it adds up. The East Pacific Rise, on the other hand, spreads much faster, at rates of 6 to 16 centimeters per year. This difference in spreading rate affects the shape of the ridge. Slow-spreading ridges tend to have steep, rugged topography with deep rift valleys. Fast-spreading ridges are gentler, broader, with less dramatic relief, but in both cases, the fundamental process is the same: plates pulling apart, magma rising, new seafloor forming. Now, not all underwater volcanoes form at spreading centers. Some form in a completely different way, in places where tectonic plates collide rather than diverge. These are called subduction zones, and they create some of the most dramatic volcanic features on the planet, both above and below the water. At a subduction zone, one tectonic plate is forced beneath another, sinking down into the mantle. This usually happens when an oceanic plate collides with another plate, either oceanic or continental. The oceanic plate, being denser, slides beneath the other in a process that can extend hundreds of kilometers into the Earth's interior. As this plate descends, it carries with it water trapped in minerals and sediments. The increasing pressure and temperature cause these minerals to release their water, and this water rises into the hot mantle rock above. Water has a remarkable effect on rock. When water is introduced into hot mantle rock, it lowers the rock's melting point, causing it to partially melt even though the temperature hasn't changed. This creates magma that is often richer in silica than the basaltic magma found at mid-ocean ridges. This magma rises through the overlying plate, and when it reaches the surface, it forms volcanoes. Sometimes these volcanoes break the ocean's surface to form island arcs, chains of volcanic islands like the Aleutian Islands or the islands of Japan. But many times they remain underwater, forming chains of submarine volcanoes that dot the seafloor. The Mariana Arc is a perfect example. Here the Pacific Plate is being subducted beneath the small Mariana Plate. The volcanoes that form are arranged in a curved line, parallel to the Mariana Trench where the subduction is happening. Some of these volcanoes are active, some are dormant, but all of them were created by this same process of one plate diving beneath another. Beneath each of these volcanoes, whether at a spreading ridge or a subduction zone, lies a magma chamber. This is essentially a reservoir of molten rock that has accumulated beneath the crust, sometimes just a few kilometers below the seafloor. These chambers can be enormous, extending for tens of kilometers horizontally. They're fed by magma rising from deeper in the mantle, and they feed the eruptions that occur at the surface. The temperature inside these magma chambers can exceed 1,200 degrees Celsius. The rock is so hot that it glows, though of course no one has ever seen this directly. The pressure is also immense, both from the weight of the rock above and from gases dissolved in the magma itself. When an eruption occurs, it's often because this pressure has overcome the strength of the overlying rock, allowing magma to force its way upward through cracks and fissures. When magma reaches the ocean floor, the environment it encounters is unlike anything on land. The water temperature at these depths is typically around 2 degrees Celsius, just barely above freezing. The pressure is several hundred times greater than at the surface. These conditions affect how the lava behaves. On land, lava flows can travel for kilometers, cooling slowly as they go. Underwater, the lava cools almost instantly on its outer surface, forming a glassy crust within seconds. But inside that crust, the lava is still molten and still flowing. This rapid cooling creates unique structures, which we'll explore more in the next section. But what's important to understand is that this process, this interaction between molten rock and cold ocean water, is happening right now at this very moment, in dozens of locations around the world. New seafloor is being created, volcanic chimneys are growing taller, lava is flowing across the ocean floor, adding to the ever-expanding crust. And all of this happens in silence, or at least in a silence that humans will never directly experience. Down there are sounds. The groaning of the Earth's crust as it splits and shifts, the hiss and crack of lava meeting water, the rumble of distant earthquakes. But these are sounds we can only record with instruments, sounds that exist in a world so remote and so alien that it might as well be another planet. Yet it's all part of our Earth, part of the same dynamic system that creates mountains and valleys, that shapes coastlines and determines where life can flourish. Deep-sea volcanoes are, in many ways, the Earth's renewal system. They recycle old crust and create new. They release heat from the planet's interior, and they provide the chemical ingredients that make life possible in some of the most unlikely places. They are ancient and ongoing, patient and persistent, shaping our world in ways both visible and invisible. One of the most distinctive features of underwater volcanic activity is something called pillow lava, and it's exactly as charming as it sounds. When you look at photographs of the ocean floor near volcanic ridges, you often see fields of rounded, bulbous rocks that look almost soft, like cushions or pillows piled on top of each other. These are pillow lavas, and they form through a process that's both elegant and fascinating. Imagine molten lava, glowing orange and liquid, flowing out of a crack in the ocean floor. The moment it touches the cold seawater, something remarkable happens. The outer surface of the lava cools instantly, so quickly that it forms a thin crust of volcanic glass within seconds. This glassy shell acts like a barrier, temporarily insulating the still molten lava inside. But lava is under pressure, and it keeps flowing, keeps pushing forward. As more lava accumulates behind that initial crust, it swells and bulges, creating a rounded pillow-like shape. Eventually, the pressure becomes too great, and the glassy crust breaks, usually at the front or tip of the forming pillow. Molten lava squeezes out through this break, and the process begins again. A new glassy crust forms. A new pillow starts to grow. This happens over and over, creating what geologists call a pillow flow, a series of interconnected bulbous structures that look remarkably organic, almost alive. Individual pillows can range in size from about 10 centimeters across to more than a meter, though most fall somewhere in between. They're not perfect spheres. Gravity and the uneven flow of lava give them irregular shapes, with the top often more rounded and the bottom somewhat flattened where it rests on whatever is beneath it. Some pillows are nearly spherical, like oversized marbles scattered across the seafloor. Others are elongated, forming tube-like structures several meters long. The shapes vary depending on how quickly the lava was flowing, how steep the slope was, and exactly how fast the cooling occurred. If you were to examine a pillow lava up close, you'd notice several distinctive features. The outer surface is glassy, smooth in places, but often cracked and textured in others. This glass, called volcanic glass or basaltic glass, forms because the lava cooled so rapidly that crystals didn't have time to grow. Inside, however, the rock is more crystalline, with a texture that reflects slower cooling. Sometimes you can see radial cracks extending from the outer edge toward the center, formed as the pillow contracted while cooling. The surface of pillows often shows other interesting features too. There might be grooves or striations where the glassy crust fractured and molten lava briefly squeezed out before cooling. There might be small buds, tiny protrusions, where pressure forced lava through weak points in the crust. Geologists call these features pillow buds, and they're one of the telltale signs that you're looking at a genuine pillow lava and not just a rounded boulder. Pillow lavas are the most common form of volcanic rock on Earth. That might surprise you, since most of us have never seen one except in photographs or museum displays. But remember, the ocean floor covers more than 70% of our planet's surface, and much of that floor is made of pillow basalts. Every spreading ridge, every submarine volcano produces these distinctive formations. They're being created right now, at this very moment, in the darkness of the deep ocean. The rate at which pillow lavas form depends on the eruption rate. If lava is flowing relatively slowly, there's time for individual pillows to form, cool, and then be buried by the next pillow in the sequence. These create the classic pillow flows that geologists love to study. But if the eruption rate is higher, if lava is pouring out more rapidly, the dynamics change. Instead of individual pillows, you might get what are called sheet flows, where lava spreads out in broad, relatively flat sheets across the seafloor. These sheet flows still cool rapidly on contact with water, but they don't have time to form the distinctive pillow shapes. At fast-spreading ridges like the East Pacific Rise, sheet flows are more common than pillow flows. The high eruption rate and gentler slopes lead to lava spreading out rather than piling up. At slow-spreading ridges like the Mid-Atlantic Ridge, pillow lavas dominate. The lower eruption rates and steeper slopes create the perfect conditions for pillows to form and accumulate. Either way, whether as pillows or sheets, this basaltic rock is building the foundation of our ocean basins. What's particularly fascinating about pillow lavas is that they can tell us stories about ancient oceans. When geologists find pillow lavas on land, in areas far from any present-day ocean, they know they're looking at rocks that formed underwater, perhaps hundreds of millions of years ago. These rocks have been uplifted by tectonic forces, exposed by erosion, and now they stand as evidence of ancient seas. You can find pillow lavas in mountain ranges around the world, remnants of ocean floor that was once deep beneath the waves but is now high and dry. The island of Cyprus, for example, has extensive outcrops of pillow lavas as part of a geological formation called an ophiolite. An ophiolite is a section of ancient ocean floor that has been thrust onto land, usually during the collision of tectonic plates. The pillow lavas in Cyprus formed in the Tethys Ocean more than 90 million years ago. Now they're exposed on hillsides, where you can walk among them and run your hands over their glassy surfaces, connecting with a volcanic past that predates human existence by unimaginable spans of time. In some places, pillow lavas stack up to form substantial structures. Near volcanic vents on the mid-ocean ridges, you might find pillow mounds that rise tens of meters above the surrounding seafloor, accumulations of countless individual pillows piled on top of each other over multiple eruptions. These mounds can be several hundred meters across, miniature undersea hills made entirely of volcanic rock. They're not permanent features. Tectonic movement and erosion will eventually break them down, but while they exist, they provide habitat for deep-sea life and record the history of volcanic activity in that location. Some of the most dramatic pillow lava formations occur on steep underwater slopes. When lava flows down an incline, the pillows elongate, forming tubes that can be several meters long. These tubular pillows often show a pattern called neck and knob structure, where the tube narrows and widens in a series of bulges, like a string of sausages. This happens because the lava inside the tube flows in pulses, each pulse creating a new bulge before the crust thickens enough to slow the flow. The color of pillow lavas can vary too, though most are some shade of dark gray or black when fresh. Over time, chemical reactions with seawater can alter the glassy surfaces, turning them brown, yellow, or even orange. A substance called palagonite, a clay-like material, forms when the volcanic glass reacts with water. This gives older pillow lavas a rusty, weathered appearance that's quite different from the dark, glassy sheen of freshly erupted ones. In every pillow lava field, you're seeing a snapshot of a moment in geological time. Each pillow represents a few minutes or hours of volcanic activity, a brief episode when molten rock met cold water and transformed. And those moments, multiplied by millions, have built the very floor of our oceans, have created the platform on which marine life depends, and have shaped the history of our planet in ways both profound and subtle. As we descend deeper into our exploration of deep-sea volcanoes, we encounter one of the ocean's most remarkable phenomena, hydrothermal vents. These are the ocean's hot springs, places where superheated water erupts from the seafloor, carrying with it a chemical soup that has traveled through the Earth's crust and been transformed by heat and pressure into something entirely different from the seawater that originally seeped down. The process begins with seawater. Through cracks and fissures in the volcanic rock of the ocean floor, cold seawater percolates downward, sometimes traveling several kilometers into the crust. As this water descends, it moves closer to the heat source, either a magma chamber or simply hot rock that's been recently solidified from magma. The temperature rises dramatically. The water, now under immense pressure from the weight of rock and ocean above it, is heated to temperatures that would boil it instantly at the surface. but down here pressure keeps it liquid even at 400 degrees Celsius or more. As the water travels through the hot rock, it becomes a powerful chemical solvent. Minerals begin to dissolve. Iron, copper, zinc, manganese, sulfur, and many other elements leach out of the surrounding rocks and enter the water. The water also becomes increasingly acidic, which helps it dissolve even more minerals. This chemically altered water is now called hydrothermal fluid, and it's buoyant because it's hot and less dense than the surrounding cold seawater. So it begins to rise, following the path of least resistance back toward the seafloor. When this superheated, mineral-rich fluid finally erupts from the seafloor through a vent, it creates a spectacular display. The fluid, which might be 300 to 400 degrees Celsius, meets seawater that's only about 2 degrees Celsius. This sudden temperature drop causes the dissolved minerals to precipitate out of solution almost instantly. They form tiny particles that cloud the water, creating plumes that look like smoke rising from a chimney. Depending on the minerals involved, these plumes can be black, white, or various shades of gray and brown. Black smokers are perhaps the most famous type of hydrothermal vent. They emit plumes that are dark, almost opaque, colored by sulfide minerals, especially iron sulfide. When you see footage of a black smoker, it looks like a factory chimney pouring dark smoke into the water, except this smoke is actually mineral particles. These vents tend to be the hottest, with fluid temperatures that can exceed 400 degrees Celsius. The minerals precipitating from black smokers include not just iron sulfide but also copper, zinc, and other metals that have significant economic value. White smokers, on the other hand, emit lighter-colored plumes. These vents are generally cooler, with fluid temperatures typically between 100 and 300 degrees Celsius. The minerals here are different, dominated by barium, calcium, and silicon compounds rather than sulfides. The plumes from white smokers can look almost ethereal in photographs, like wisps of white or pale gray smoke drifting up through the water. Over time, the minerals precipitating from these vents don't just dissolve into the ocean. They accumulate around the vent opening, building up layer by layer to form chimney-like structures. These hydrothermal chimneys are among the most striking features of the deep ocean floor. They can grow remarkably quickly. Some chimneys have been observed to grow several centimeters per day during active venting. Over years or decades, they can reach heights of 20, 30, even 50 meters or more. The tallest known hydrothermal chimney, nicknamed Godzilla, stood about 15 stories tall before it eventually collapsed. These chimneys aren't simple tubes. They're complex structures with multiple passages, branches, and chambers. The interior of an active chimney can be extremely hot, with temperatures exceeding 300 degrees Celsius where the hydrothermal fluid is flowing through. The outer walls of the chimney, however, are bathed in cold seawater, so there's an incredible temperature gradient across just a few centimeters of rock. This creates different mineral zones within the chimney, with different minerals crystallizing at different temperatures. The minerals that make up these chimneys can be quite beautiful. Iron sulfide forms black, metallic-looking crystals. Copper sulfide can have a brassy appearance. Some chimneys contain minerals like chalcopyrite, which has a golden color, or bornite, sometimes called peacock ore for its iridescent blue and purple surface. There are even reports of hydrothermal chimneys containing trace amounts of gold and silver, though these are rare and not concentrated enough to be worth mining, at least not yet. Not all hydrothermal vents form tall chimneys. Some create low mounds or cones, others are more diffuse, with warm water seeping up through a field of cracks rather than jetting from a single opening. These diffuse flow areas can be extensive, covering hundreds of square meters of seafloor with warm, chemically altered water. The water here is usually much cooler than at the focused vents, perhaps only 10 to 50 degrees Celsius above ambient, but it still carries dissolved chemicals and still supports unique communities of life. One particularly unusual type of vent is found at a place called the Lost City Hydrothermal Field in the Atlantic Ocean. Unlike most vents, which are driven by recent volcanic activity, the Lost City vents are powered by chemical reactions between seawater and mantle rock. These vents are cooler, typically below 90 degrees Celsius, and they emit fluids that are highly alkaline rather than acidic. The chimneys here are made of calcium carbonate and magnesium hydroxide, giving them a white or pale gray appearance. Some of these structures are over 60 meters tall, and they're thought to be thousands of years old, much older than typical black smoker chimneys. The locations of hydrothermal vents are closely tied to volcanic and tectonic activity. Most vents occur along mid-ocean ridges, where the crust is thin and magma is close to the surface. But they're also found at back arc basins, where seafloor spreading occurs behind volcanic island arcs, and even in some submarine volcanoes that aren't directly associated with plate boundaries. Anywhere there's heat and fractures in the seafloor, there's potential for hydrothermal vents to form. Scientists estimate that there may be thousands of active hydrothermal vent sites in the global ocean, though only a few hundred have been discovered and studied. Each discovery brings new surprises, new mineral compositions, new biological communities. Some vents are small and short-lived, lasting only a few years before the underlying volcanic activity shifts or stops. Others persist for decades or even centuries, steadily building their mineral structures and supporting thriving ecosystems. The deepest known hydrothermal vents are in the Cayman Trough in the Caribbean Sea, at a depth of nearly 5,000 meters. At such depths, the pressure is almost 500 times greater than at sea level. The challenges of exploring these environments are immense, requiring specialized equipment and submersibles that can withstand the extreme pressure. Yet the rewards are equally great, as each new vent field reveals more about how our planet works and how life adapts to extreme conditions. Perhaps what's most striking about hydrothermal vents is their sheer energy. The total heat output from all the hydrothermal vents in the ocean is substantial, estimated to account for about 20% of Earth's total heat loss. This is heat that originated deep within the planet, carried up through the mantle and crust and released into the ocean. In a very real sense, hydrothermal vents are direct windows into Earth's interior, places where you can see and measure processes that normally happen far below our feet. And in the midst of all this heat and chemistry and mineral precipitation, life has found a way to not just survive but thrive, which brings us to one of the most remarkable chapters in the story of deep-sea volcanoes. Until 1977, scientists believed that the deep ocean floor was a desert, a cold, dark, nutrient-poor environment where life was scarce and survival was marginal. The prevailing view was that all life on Earth ultimately depended on photosynthesis, on the ability of plants and algae to capture energy from sunlight and convert it into food. In the deep sea, where no sunlight penetrates, life was thought to depend entirely on organic matter falling from above, the so-called marine snow of dead organisms and waste products drifting down from the sunlit surface layers. Then, in February of 1977, a group of scientists exploring the Galapagos Rift, a volcanic spreading center near the Galapagos Islands, made a discovery that would fundamentally change our understanding of life on Earth. Using the deep-sea submersible Alvin, they descended to a depth of about 2,500 meters to investigate temperature anomalies they'd detected in the water. What they found there was so unexpected, so extraordinary, that it challenged everything they thought they knew. Clustered around hydrothermal vents on the seafloor, they found dense communities of large animals, giant clams, mussels, crabs, and most startling of all, huge tube worms. Some of them over 2 meters long, with brilliant red plumes extending from white tubes anchored to the rock. The water around these vents was warm, shimmering with heat, and rich in chemicals. But there was no sunlight, no photosynthesis, no obvious source of food, and yet life was abundant, thriving in what should have been a barren wasteland. The key to this mystery lies in a process called chemosynthesis, and at its heart are bacteria, microscopic organisms with remarkable abilities. These bacteria, along with archaea, another group of microorganisms, are capable of using chemical energy instead of light energy to produce organic compounds. Specifically, they use chemicals like hydrogen sulfide, which pours out of hydrothermal vents in large quantities, as an energy source. By oxidizing these chemicals, the bacteria can convert carbon dioxide and water into sugars and other organic molecules, just as plants do through photosynthesis, but without any need for sunlight. This might sound simple, but it's actually quite complex. The bacteria have specialized enzymes that can handle hydrogen sulfide, which is toxic to most organisms. They're also adapted to live in extreme temperature gradients, where the water can vary from near freezing to over 100 degrees Celsius across just a few centimeters. Some species of bacteria form mats on the rocks around vents, covering surfaces with white, yellow, or orange films. Others live freely in the water or attach themselves to mineral surfaces. But the real magic happens when these bacteria form symbiotic relationships with larger animals. Many of the creatures living around hydrothermal vents don't actually feed on the bacteria directly. Instead, they house the bacteria inside their own bodies, providing them with shelter and a steady supply of the chemicals they need, and in return, the bacteria provide the animals with food. Giant tube worms are perhaps the most famous example of this symbiosis. These remarkable creatures, members of the genus Riftia, have no mouth, no gut, no digestive system at all. As adults, they're completely dependent on the bacteria living inside them. The tube worm has a specialized organ called a trophosome, which is packed with billions of chemosynthetic bacteria. The worm's bright red plume, which extends from its tube, is not for feeding but for gas exchange. It absorbs oxygen from the seawater and also absorbs hydrogen sulfide, both of which are then transported by special hemoglobin molecules to the bacteria in the trophosome. The bacteria use the hydrogen sulfide as an energy source to convert carbon dioxide into organic compounds, and these compounds are then shared with the tube worm. It's a perfect partnership. The bacteria get a safe place to live and a steady supply of chemicals, and the worm gets all the nutrition it needs without ever eating in the conventional sense. This relationship is so efficient that tube worms are among the fastest growing invertebrates on Earth, capable of growing nearly 2 meters in length in just a few years. Giant clams found at hydrothermal vents have a similar arrangement, unlike their shallow water cousins that feed by filtering plankton from the water. Vent clams house chemosynthetic bacteria in their gills. These bacteria, like those in tube worms, convert chemical energy into food, which the clam then absorbs. Some species of clams can grow to over 30 centimeters in length, enormous for deep-sea organisms, and they can live for decades or even centuries in the nutrient-rich environment around vents. Mussels are another group of vent animals that rely on bacterial symbionts. The mussels in hydrothermal vent communities, species like Bathymodiolus, have bacteria living in their gill tissue. These bacteria can be quite versatile, with some species hosting 2 different types of bacteria, one that oxidizes sulfides and another that oxidizes methane. This gives the mussels flexibility in where they can live and what chemical environments they can tolerate. Vent mussels are found in hydrothermal vent systems around the world, from the Atlantic to the Pacific to the Indian Ocean, and they're often among the most abundant animals in these communities. Not all vent animals depend on symbiotic bacteria. Some are predators or scavengers, feeding on the abundant life that the chemosynthetic bacteria support. Vent crabs, for example, are often seen picking at tube worms or scavenging dead animals. There are fish species adapted to life near vents, their bodies able to tolerate the warm water and low oxygen levels. There are shrimp that swarm around some vents in enormous numbers, some species actually farming bacteria on specialized appendages on their bodies. One particularly fascinating creature is the yeti crab, discovered in hydrothermal vent fields in the Pacific Ocean. This white, furry-looking crab has long, hairy arms that are covered in filamentous bacteria. The crab appears to farm these bacteria, waving its arms in the vent fluids to provide the bacteria with the chemicals they need, and then eating some of the bacteria for food. It's a form of agriculture practiced in one of the most extreme environments on Earth. The Pompeii worm is another marvel of adaptation. This polychaete worm lives in tubes attached to the sides of hydrothermal chimney walls, in areas where temperatures can fluctuate wildly. Its tail can be in water as hot as 80 degrees Celsius, while its head extends into cooler water around 20 degrees Celsius. The worm tolerates this incredible temperature gradient, making it one of the most heat-resistant complex animals known. It too has bacteria living on its back, forming a fuzzy coat that may provide additional insulation or food or both. These vent communities are among the most productive ecosystems in the deep sea. While most of the deep ocean floor supports only sparse life, vent fields can have biomass densities rivaling or exceeding those of tropical coral reefs. The abundance of chemical energy from the vents, converted into biological energy by bacteria, supports food webs that are both complex and resilient. But these ecosystems are also ephemeral. Hydrothermal vents don't last forever. Volcanic activity shifts, magma chambers cool, tectonic movements seal off fluid pathways. A vent that's flourishing today might go extinct in a few years or decades. When a vent dies, the community it supported dies with it. The tube worms, unable to move and completely dependent on the chemicals from the vent, simply perish. Their white tubes remain, standing like gravestones on the now cold seafloor, gradually being colonized by other organisms that don't depend on vent chemistry. But new vents are constantly forming. Volcanic eruptions create new sites where hydrothermal circulation can begin, and somehow the animals find these new vents and colonize them. Many vent species have larval stages that drift in ocean currents, sometimes for months, searching for the chemical signals that indicate a new vent. When they find one, they settle and begin the cycle anew. It's a form of island biogeography, except the islands are ephemeral hotspots on the ocean floor, and the ocean between them is vast and cold. The discovery of hydrothermal vent ecosystems fundamentally changed biology. It showed that life doesn't necessarily require sunlight, that chemosynthesis can support entire ecosystems just as photosynthesis does. This has profound implications for the search for life elsewhere in the universe. If life can thrive around hydrothermal vents on Earth, perhaps similar life exists in the oceans believed to exist beneath the ice of Europa, Jupiter's moon, or Enceladus, Saturn's moon. These worlds have no sunlight reaching their oceans, but they likely have hydrothermal vents powered by tidal heating. Life there, if it exists, might look very different from anything on Earth, but the fundamental principle, chemical energy supporting biological systems, could be the same. And so, in these dark, hot, chemically extreme environments, we find some of the most remarkable and resilient life on our planet. We find ecosystems that challenge our assumptions and expand our understanding of what's possible. We find beauty in tube worms' crimson plumes and wonder in the tiny bacteria that make it all work. The volcanic deep, far from being a lifeless desert, is an oasis, a testament to life's extraordinary ability to adapt, persist, and flourish in the most unlikely of places. The Mariana Arc and Pacific volcanic activity. The Western Pacific Ocean is home to some of the most dramatic submarine volcanic features on Earth. Here, where the vast Pacific plate is being subducted beneath smaller plates, chains of underwater volcanoes rise from the ocean floor, forming arcs that stretch for thousands of kilometers. One of the most studied and most fascinating of these is the Mariana Arc, a chain of more than 40 submarine volcanoes extending north from the island of Guam. The Mariana Arc sits above one of the deepest subduction zones in the world. Just to the east of the arc lies the Mariana Trench, where the Pacific plate plunges beneath the Mariana Plate, descending into the mantle at one of the steepest angles found anywhere on Earth. The deepest point in the ocean, the Challenger Deep, is found here, at a depth of nearly 11,000 meters below the surface. It's a place of extremes, where the pressure is over 1,000 times greater than at sea level, and where the physics and chemistry of the ocean operate in ways we're still working to understand. As the Pacific plate descends into the trench, it carries with it water trapped in sediments and minerals. As the plate heats up, this water is released and rises into the mantle above, lowering its melting point and creating magma. This magma, rich in volatiles and often more silica-rich than typical mid-ocean ridge basalt, rises through the overlying plate and erupts, forming volcanoes. Some of these volcanoes break the surface to form islands. Many others remain underwater, their peaks still hundreds or thousands of meters below the ocean's surface. The submarine volcanoes of the Mariana Arc are incredibly diverse. Some are tall, conical seamounts rising 3,000 meters or more from the seafloor. Others are lower, broader features with multiple vents and craters. Some are actively erupting, others are dormant but still hydrothermally active, and still others are completely extinct, their summits eroded and colonized by deep-sea corals and sponges. One particularly well-studied volcano in the Arc is NW Rota 1, which was discovered to be actively erupting during an expedition in 2006. This was the first time scientists had ever witnessed an underwater volcanic eruption in progress. The submersible captured video of lava being ejected from a vent on the volcano's summit, glowing orange and red even at a depth of over 500 meters. The eruption was creating massive clouds of volcanic ash and altered water that rose hundreds of meters into the ocean above. It was a reminder that these volcanoes, hidden beneath the waves, are just as dynamic and powerful as their terrestrial counterparts. Another fascinating feature of the Mariana Arc is the Morgue caldera, a massive underwater crater formed by the collapse of a volcanic summit. The caldera is several kilometers across and hundreds of meters deep, and its floor and walls host numerous hydrothermal vents. Expeditions to Molk have discovered extensive vent fields with thriving biological communities, including dense aggregations of shrimp, mussels, and other vent-dependent organisms. What makes the Mariana Arc particularly interesting to scientists is its diversity of volcanic and hydrothermal activity. Different volcanoes in the arc emit different types of fluids, with different chemical compositions and different temperatures. Some vents are sulfide-rich black smokers. Others emit fluids dominated by carbon dioxide or even molten sulfur. One volcano, called NW Ifuku, has vents that emit liquid carbon dioxide, which is stable at the pressure and temperature found at that depth. These liquid CO2 vents create shimmering pools on the seafloor, a sight unlike anything else in the ocean. The biological communities at different vent sites in the Mariana Arc also vary considerably. Some sites are dominated by mussels, others by tube worms, still others by shrimp or gastropods. The reasons for these differences aren't always clear, but they likely relate to the specific chemistry of the vent fluids, the temperature and stability of the venting, and the history of colonization. Each vent field is in some sense a unique experiment in how life adapts to extreme conditions. Beyond the Mariana Arc, the Pacific Ocean is dotted with thousands of other submarine volcanoes. The seamount chains of Hawaii and the Emperor Seamounts, stretching across the northern Pacific, are the products of a hot spot, a plume of hot mantle material that has been creating volcanoes for millions of years as the Pacific Plate moves over it. The oldest seamounts in this chain are over 70 million years old, now heavily eroded and far from their source. Along the East Pacific Rise, one of the fastest spreading mid-ocean ridges in the world, volcanic activity is almost continuous. Fresh lava flows cover the seafloor, black and glassy, unweathered by time. Hydrothermal vents here are numerous and dynamic, with some vents erupting, others waning, and the patterns shifting over years and decades. Scientists have established long-term monitoring stations at some East Pacific Rise sites, tracking changes in vent activity, water chemistry, and biological communities over time. The Juan de Fuca Ridge, off the coast of the Pacific Northwest, is another intensely studied volcanic system. It's smaller and slower spreading than the East Pacific Rise, but it's more accessible to researchers. The ridge has several well-known vent fields, including the Endeavour segment, which hosts spectacular black smoker chimneys and dense biological communities. One chimney at Endeavour, called Godzilla, reached a height of over 40 meters before it toppled in the late 1990s. In all these places, the story is the same. Volcanic activity drives hydrothermal circulation, which supports unique ecosystems, which in turn attract scientific attention and help us understand the connections between geology, chemistry, and biology. The Pacific Ocean, being the largest and most volcanically active ocean basin, offers countless opportunities for discovery and study. And yet, despite decades of research, we've only scratched the surface. Most of the Pacific's submarine volcanoes have never been visited. Most of its hydrothermal vents remain undiscovered. Each expedition brings new findings, new species, new insights into how our planet works. The deep volcanic systems of the Pacific are a frontier, a realm of ongoing exploration where mysteries outnumber answers and where every dive has the potential for discovery. The slow dance of creation. Deep beneath the ocean's surface, in the darkness and cold, a slow but inexorable dance is taking place. It's the dance of creation, of new seafloor being born, of continents drifting apart, of ocean basins widening. This process, called seafloor spreading, is so gradual that you'd never notice it in a human lifetime, but over geological time, it has reshaped the entire surface of our planet. At mid-ocean ridges, tectonic plates are moving apart from each other. The rate varies from place to place. At the slowest ridges, like parts of the mid-Atlantic ridge, the separation is only about 2 centimeters per year, roughly the rate at which your fingernails grow. At faster ridges, like the East Pacific Rise, the plates separate at 15 centimeters per year or more. These might seem like tiny distances, but they add up. Over 1 million years, even the slowest spreading ridge will create 20 kilometers of new seafloor. Over 100 million years, that becomes 2,000 kilometers. This new seafloor isn't created all at once. Instead, it's formed in episodes. in bursts of volcanic activity that might last days or weeks, followed by periods of relative calm that might last years or decades. Magma rises from the mantle, intrudes into the crust, and sometimes erupts onto the seafloor. Each eruption adds a new layer of rock, building up the ocean floor bit by bit. The structure of the oceanic crust reflects this process. At the very top is a thin layer of pillow lavas and sheet flows, the most recent volcanic rocks. Below that is a layer called the sheeted dike complex, where vertical sheets of magma intruded into older rock. Below that are gabbros, coarse-grained igneous rocks that crystallize slowly from magma chambers. And at the bottom, forming the transition to the mantle, are rocks that were once part of the mantle but have been altered by interaction with seawater and partial melting. The entire sequence, from top to bottom, is typically only about 6 or 7 kilometers thick, much thinner than continental crust. As new seafloor forms at the ridge, older seafloor moves away, sliding down the flanks of the ridge and onto the abyssal plains. This older crust gradually cools, contracts, and subsides, becoming denser as it ages. The oldest parts of the ocean floor, far from any ridge, sit at depths of 5,000 or 6,000 meters, much deeper than the ridges where they formed. The age of oceanic crust can be determined by measuring the magnetic properties of the rocks. When basalt crystallizes from magma, iron-bearing minerals in the rock align with Earth's magnetic field, recording the direction of that field at the time the rock formed. Earth's magnetic field reverses periodically, with the north and south magnetic poles swapping places. These reversals happen irregularly, sometimes every few 100,000 years, sometimes after millions of years. The pattern of normal and reversed magnetism in oceanic crust creates stripes parallel to the mid-ocean ridges that mirror on either side of the ridge. By mapping these magnetic stripes and comparing them to the known history of geomagnetic reversals, scientists can determine the age and spreading rate of any part of the ocean floor. The oldest oceanic crust currently known is in the western Pacific, near Japan. It's about 180 million years old, dating back to the Jurassic period, when dinosaurs walked the Earth. This might seem ancient, but it's actually young compared to continental crust, which can be billions of years old. The reason for this difference is subduction. Oceanic crust, being denser than continental crust, eventually gets recycled back into the mantle at subduction zones. The oldest oceanic crust is the stuff that hasn't yet been subducted, but eventually it too will be consumed. The average age of oceanic crust is less than 100 million years, a blink of an eye in geological terms. This constant cycle of creation and destruction means that the ocean floor is always changing. The Atlantic Ocean, for example, is getting wider as the Americas drift away from Europe and Africa. It's grown by several thousand kilometers since it first began to open about 200 million years ago, and it continues to widen by a few centimeters each year. Conversely, the Pacific Ocean is shrinking as oceanic crust is subducted at its margins faster than new crust is created at its ridges. Millions of years from now, the Pacific will be smaller than it is today, and the Atlantic will be larger. These movements have profound effects on climate, on ocean circulation, on the distribution of life. The opening and closing of ocean basins changes how water moves around the planet, which affects global temperature and weather patterns. The eruption of underwater volcanoes releases chemicals into the ocean that can alter ocean chemistry on regional or even global scales, and the heat released from hydrothermal vents adds to the ocean's total heat budget, a small but measurable contribution. What's particularly striking is how efficient this system is. Despite the incredible temperatures involved, despite the violence of volcanic eruptions and tectonic collisions, the overall process is remarkably stable. The mid-ocean ridge system has been operating in more or less the same way for hundreds of millions of years. The mechanisms that drive plate tectonics, convection in the mantle, heat from radioactive decay, gravity pulling dense plates downward, all work together in a balanced system that continuously recycles the ocean floor. And it all happens in silence, or at least in a silence that reaches no human ears. Down there, 2,000 or 3,000 meters below the surface, lava flows across the seafloor, cooling and solidifying. Volcanic gases bubble up through cracks. Tectonic plates grind past each other with a low, continuous rumble. But there's no one there to hear it, no one to witness it except the occasional scientific expedition. It's a process so vast and so slow that it defies our everyday understanding of time and change. Yet it's also intensely active. intensely dynamic. At this very moment, somewhere along the 65,000-kilometer length of the mid-ocean ridge system, magma is erupting. New seafloor is forming. The dance continues, patient and unstoppable, reshaping the planet one eruption at a time. As we near the end of our journey through the volcanic deep, it's worth pausing to consider a profound question. Could these environments, these hydrothermal vents on the ocean floor, be where life itself began? It's a question that has captivated scientists since the discovery of vent ecosystems in the late 1970s. And while we don't have definitive answers, the evidence is compelling enough that many researchers consider hydrothermal vents to be among the most likely birthplaces of life on Earth. When life first appeared on our planet, perhaps as much as 4 billion years ago, the Earth was a very different place. The atmosphere contained little or no oxygen. The sun was slightly dimmer than it is today. The surface was heavily bombarded by asteroids and comets, making it a hostile environment for any fragile organisms. The shallow oceans, if they existed, would have been subject to this bombardment and to intense ultraviolet radiation from the sun, which could damage or destroy delicate organic molecules. But deep in the ocean, protected by thousands of meters of water, conditions were more stable. Hydrothermal vents would have existed back then, just as they do today, wherever volcanic activity and circulating seawater came together. These vents would have provided chemical energy in the form of hydrogen, hydrogen sulfide, and other reduced compounds. They would have created temperature gradients, with hot fluid mixing with cold seawater, providing a range of conditions where different chemical reactions could occur, and they would have provided mineral surfaces, such as iron sulfide minerals, that could act as catalysts for organic chemistry. Some scientists have proposed that the first self-replicating molecules, the earliest ancestors of modern life, formed at hydrothermal vents. The chemical conditions at vents are favorable for the synthesis of simple organic compounds. Laboratory experiments have shown that reactions similar to those occurring at vents can produce amino acids, the building blocks of proteins and nucleotides, the building blocks of DNA and RNA. The mineral surfaces at vents could have concentrated these molecules and facilitated their assembly into more complex structures. One particularly compelling hypothesis involves alkaline hydrothermal vents, like those found at the Lost City hydrothermal field. These vents produce fluids that are high in pH and rich in hydrogen. When this alkaline fluid meets the slightly acidic ocean water, it creates natural chemical gradients across thin mineral barriers in the vent structures. Some researchers have suggested that these gradients could have been used by the earliest proto-cells, providing a primitive form of energy that preceded the more sophisticated energy systems used by modern cells. In essence, the vent structures themselves could have functioned as natural chemical reactors, concentrating reactants, facilitating reactions, and providing energy, all without requiring the complex biological machinery that modern cells possess. Another line of evidence comes from studying the most ancient lineages of life. When scientists construct evolutionary trees based on genetic data, trying to trace back to the common ancestor of all life, they often find that the deepest branches of these trees contain organisms that thrive in hot, oxygen-free environments. Many of these organisms are thermophiles and hyperthermophiles, bacteria and archaea, that live in hot springs or around hydrothermal vents. This suggests that the common ancestor of all life might have been a thermophile, adapted to the hot, chemically rich environments found at vents. Of course, not all scientists agree that life began at hydrothermal vents. Some favor other environments, such as shallow pools on land or the interface between ice and liquid water, or even the surfaces of clay minerals far from any volcanic activity. Each hypothesis has its strengths and weaknesses, and the question of life's origin remains one of the great unsolved mysteries in science. But regardless of where life began, the discovery that entire ecosystems can thrive without any dependence on sunlight has profound implications. It means that photosynthesis, while crucial for most life on Earth today, is not a requirement for life in general. Chemosynthesis can do the job just as well, at least in environments where the right chemicals are available. This expands the range of places where we might find life, both on Earth and elsewhere in the universe. Consider Jupiter's moon Europa. Beneath its icy crust lies a global ocean, perhaps 100 kilometers deep. This ocean has no sunlight. It's covered by kilometers of ice and is far from the sun. But Europa experiences intense tidal heating as it orbits Jupiter, flexing and squeezing under the giant planet's gravitational pull. This heating could power volcanic activity on the ocean floor, creating hydrothermal vents not unlike those on Earth. If such vents exist and if the chemistry is right, there's no reason in principle why life couldn't exist there, thriving in the darkness just as it does in Earth's deep oceans. Saturn's moon Enceladus is another intriguing possibility. Geysers of water vapor and ice particles erupt from cracks near its south pole, indicating a subsurface ocean heated by tidal forces. Analysis of these plumes has detected organic molecules and molecular hydrogen, suggesting that water-rock reactions, possibly at hydrothermal vents, are occurring beneath the ice. Again, these are conditions that could support life. Even Mars, though it has no liquid water on its surface today, may once have had hydrothermal systems. Ancient Martian rocks show mineral deposits that resemble those found at terrestrial hot springs and hydrothermal vents. If life ever arose on Mars, it might have done so in these environments, and it's even conceivable that microbial life could persist in subsurface aquifers or hydrothermal systems on Mars today. So the volcanic deep, these dark, hot, chemically extreme environments at the bottom of our oceans, are not just curiosities, they're windows into the early Earth, into the conditions that may have given rise to life. They're laboratories where we can study how chemical energy can support biological systems, and they're analogues for environments that might exist on other worlds, places where life could conceivably arise and thrive. In exploring the deep-sea volcanoes, we're not just learning about our planet's geology or its biology, we're asking fundamental questions about the nature of life itself, about where it comes from and where else it might exist. And in that sense, every dive to a hydrothermal vent, every sample collected, every new species discovered, is a small step toward answering those deepest of questions. And so our journey through the volcanic deep comes to a gentle close. We've descended from the sunlit surface down through the darkness, down to where the Earth's crust splits and heals, where fire meets water, where life blooms in the least expected places. We've seen pillow lavas forming their cushioned shapes, hydrothermal chimneys towering like cathedrals of mineral, and creatures adapted to conditions that would seem impossible to most life on Earth. We've explored the mid-ocean ridges that wrap around the planet, the subduction zones where oceanic crust descends into the mantle, the volcanic arcs that rise from these collisions. We've learned about black smokers and white smokers, about chemosynthesis and symbiosis, about tube worms that have no mouths and giant clams that house billions of bacteria. We've touched on the possibility that these vents might be where life itself began, and we've considered the implications for life elsewhere in the universe. But more than facts and figures, more than temperatures and depths, we've glimpsed a world that reminds us how little we truly know about our own planet. 3/4 of Earth is covered by ocean, and most of that ocean remains unexplored, unmapped, unseen by human eyes. Down there in the darkness, volcanic fires burn, new seafloor is created, and ecosystems thrive in conditions that challenge every assumption we might make about where and how life can exist. It's a humbling thought, but also a comforting one. Our planet is vast and mysterious, full of hidden wonders, and we have barely begun to explore them. There are secrets in the deep waiting to be discovered, and the process of discovery continues, slowly and patiently, one expedition at a time. As you rest now, as your breathing slows and your mind drifts towards sleep, perhaps you can imagine yourself descending once more into those depths, not in a submersible, not with lights and instruments, but in your mind's eye, peacefully, calmly, floating down through layers of water that gradually darken from blue to indigo to black. You feel no pressure, no cold, only a gentle, weightless peace. Below you, the seafloor appears, dimly at first, then more clearly as imagined lights illuminate it. You see fields of pillow lava, their rounded forms stretching into the distance like frozen waves. You see a hydrothermal chimney in the distance, its plume of dark water rising lazily into the ocean above. Around its base, you see the tube worms, their red plumes swaying gently in invisible currents, and clusters of white clams dotting the rocks, and perhaps a crab picking its way delicately across the volcanic stone. It's peaceful here, in this imagination, in this quiet place where volcanic fire and ocean water meet. There's no danger, no pressure, no discomfort, only the slow, steady rhythm of creation, The patient building of new seafloor, the quiet dance of molecules and minerals and living things. The earth breathes here, slowly, deeply, its inner heat finding release, its chemical cycles continuing their ancient rounds. And as you float in this imagined space, you feel your own breathing match that deeper rhythm, slow, steady, peaceful. The volcanic deep is far away, separated from you by distance and time, and the simple impossibility of being there, but in another sense it's not far at all. It's part of the same planet you call home, part of the same system of air and water and rock that supports all life, including yours. The atoms in your body were forged in stars and dispersed through space, just as the atoms in those volcanic rocks were. The water in your cells passed through volcanic vents billions of years ago, perhaps when life itself was just beginning. You are connected to all of it, to the volcanic deep and the sunlit surface, to the tube worms and the bacteria, to the slow spreading of the seafloor and the patient building of new mountains beneath the waves. Rest now. Let the thoughts and images fade. Let the darkness be gentle and welcoming. The volcanic deep will still be there tomorrow, still creating, still hosting its strange and wonderful life, still holding its mysteries. But for now, for this night, you can simply rest, knowing that the world is vast and full of wonders, that discovery continues, and that sometimes the most profound journeys are the ones that help us fall peacefully asleep. If you enjoyed this journey to the volcanic deep, if it helped you relax and find peace, consider subscribing to Deep Sleep Seas. There are more explorations to come, more gentle journeys through the ocean's mysteries, more quiet facts to carry you into sleep. But for now, rest well. Sleep deep. Dream of pillow lavas and black smokers, of tube worms swaying in warm currents, of the slow, patient creation of new seafloor in the darkness far below. Dream of a world still being made, still being discovered, still full of wonder. Good night.